Okay, let's take a look at this interesting linear DE. First off, before we get into it, I want to note a couple of things. I think it should be pretty obvious that the constant function y equals 1 is a solution. I mean, take a look at it. Y equals 1, y prime then would be 0. 0 plus cosine times 1 equals cosine. Check. Clearly a solution. Now, in the real world, if somebody hands you a DE, they just make up some random differential equation, there's a very good chance you're not going to be able to solve it. The techniques we are learning in this class are actually pretty specialized. Like this happens to be a linear first order DE. We could solve this particular one here using an integrating factor, but that's not always going to happen. I could easily change this guy over here, and there'd be no way we could solve this. So a lot of times what happens in the real world, somebody hands you a DE. A lot of times you just guess and check. A lot of times you have to use power series, which is going to be the last thing we learn this semester. But let's say we were handed this and we would just wanted to try guess and check. So maybe a couple of things we might try. We know y equals 1 is a solution, so maybe we might try, well, I wonder if any constant would work. Y equals c. Maybe y equals 5, right? Maybe it works for any constant. But we'll see pretty quickly derivative of a constant is 0. So I would get here, if I tried to plug that in, 0 plus cosine of x times some constant c must be cosine of x. That's only going to work if c equals 1. So no, if c were 5, that wouldn't work. And you could try other things. You could maybe try, if we were just doing guess and check, maybe we know we got to have this 1 in there. Maybe you might try 1 equals, or y equals 1 plus x to some power. Maybe x squared, x to the third. Well, you could try these on your own. Pause if you want. Try 1 plus x squared, plug it into the DE, and see if that is a solution. It's not. So I'm not going to go through a whole bunch of possible things we could try. The very first time I recorded this video, I'm re-recording it. I did. I tried a whole bunch of different things, and we finally kind of figured out something that would work. I just want to point out that in the real world, that happens a lot where you just guess and check until you find something that works. And we use that technique later on in this semester in a method called undetermined coefficients. Okay, let's solve this guy as a linear DE. So let me rewrite him here so we have him in front of us. All right, so we are thinking of this in the form y prime plus some p of x times y equals some g of x. Sometimes I call this guy over here q instead of g. Who cares? Remember our integrating factor, mu of x, is e raised to the antiderivative of p of x dx. So that will be e raised to the antiderivative of cosine of x dx, which will be e to the sine of x. That's my integrating factor here. Then we multiply everything, both sides, by the integrating factor. This is our procedure. Don't forget to multiply the other side. Then, if we've done our job correctly, the left-hand side should be the product rule derivative of y times the integrating factor. If it's not, you've done goofed. I'm just recopying everything here, and we're going to check that. If I take the product rule derivative here, remember y is a function of x. So derivative of the first leave the second alone, plus leave the first alone. Derivative of e to the sine x is e to the same thing times derivative of sine. We pick up a cosine. It is correct. You always have to check that. If you don't check this step, you're going to make some mistakes. Okay, then we integrate both sides. We rewrite the left side in this form, and we integrate both sides dx. It is required that you write down that dx there. If you don't, you're writing mathematical nonsense. You'll never have an integral without a differential. Over here, the antiderivative of the derivative, those cancel out, leaving just y times the integrating factor. Now, look at the other side. I'm calling this one an interesting example because when you're looking at it at the beginning, you're like, oh, there happens to be a cosine over there. That's cool. If that wasn't a cosine right there, we would be stuck right here. Just because we can get to this step does not mean we can solve the DE. That's the point I really want to hammer home here. Just because you get to this step does not mean you can solve the DE. A lot of times you get something here and you're like, I don't know that antiderivative. And we'll look at an example in a minute. But here we do. That's just a simple u sub. So like, well, I'll write out the steps here. U is sine of x. Du is cos x. Dx. So this is really antiderivative e to the u du, which is just e to the u. So we get the plus c. So we get here e to the u plus c. And now we want to divide both sides by that guy. If the question said leave your answer in implicit form, we would be done. This is an implicit solution. And you'll have some questions that say that, especially on like the written tests. Implicit means you have not explicitly solved for y. But now let's do that. Let's find an explicit solution. Explicit just means you have y equals stuff. So like I could just write this plus c all over e to the sine. That would be perfectly fine. But I think this is going to be prettier if we write this as 1 plus c e to the negative sine of x. So what I've really done here is multiplied everything, both sides, by e to the negative sine of x, which cancels out this guy and that guy. And there is our explicit solution. It's y equals junk. That's what makes it explicit. And eventually, back up here when we were doing this guessing and checking, like maybe we would have eventually guessed that if we didn't try this integrating factor. Okay, last thing I want to point out here. Now imagine, think about, let's say, consider y prime plus cosine of xy equals, and we could literally put anything over here. I don't know, 7. Even something as simple as a constant. We'd still get the same thing. Our integrating factor is still e to the sine x. That wouldn't change. We would still get down to this step. We'd multiply everything by the integrating factor. The only thing that would change right here we would have to do this integral. We integrate both sides. Don't forget your dx. I don't know this guy's antiderivative. Neither do you. If you write down a function using elementary functions, using polynomials, rational functions, sines, trig functions, exponentials, and logs, no matter how complicated you write down that function, you can take its derivative, guaranteed. You personally have the skills to take that derivative. It exists, and you know how to take its derivative, just using product rule, quotient rule, and chain rule. It doesn't work both ways. We can very easily write down antiderivatives, write down integrals that do not have simple closed form antiderivatives using elementary functions. And this is one. Like this guy's antiderivative cannot be written down in a finite number of steps. Another classic example of that, you should have seen this in Calc 2. This antiderivative literally cannot be written down in a finite number of steps using just elementary functions, polynomials, rationals, sines and cosines, logs, and exponentials. So in this class, if you ever get to here and it's like, oh, that's something whose antiderivative just does not exist using elementary functions, you've probably goofed. Okay, that's a good place to stop.